Now what we are going to do is, we are going to look at more levels, many levels. What do I mean by looking at many levels? So till now we have looked at if there was one person who is infected and this person has some children, how the disease is going to spread in this case according to what is the number of children this person has and how is the pathogen, what is the contagiousness of the pathogen. We have looked at that in terms of probability. Now what I'm going to do is, we are going to look at this network in terms of many levels. So this is the first node here, and let's say this node here has got k children, and each of these k children is again having some k children. Each of these k children has these k children, and so on. Each of these k children are again having some k children. So what do you think? So let's call this particular level to be level 1. So this is your level 1. So what do you think are the number of people present at level 1? And we know it very clearly, this is k, because our node here, it is having k people. So the number of people at this level are going to be k people. Okay. Now what do you think is the number of people at this second level? So this is our level 2. So what is the number of people here at level 2? So a little bit of math tells us what is the number of people. So in the previous level we were having k people, and each of these k people have k children. So how many people here we have? K plus k plus k times, which is equal to k square. Similarly, let's look at level 3. So how many people will be here at level 3? So at level 2 we were having here, at level 2 we were having k square people, and each of these k square people now are having k children. Hence at level 3 we have how many people? K plus k square times, because each of these k square people are having k children each. So we get an answer k cube. So on and so forth. So if I ask you the question, what is the number of people at level I? So what it will be? At level 1 we had k people, k to the power 1. At level 2 we had k square people, k to the power 2. At level 3 we had k to the power 3. Similarly at level I we are going to have k to the power I people. So we have looked at how the at different levels, how do the number of people increase. What we want to do next is, let's look at how the contagion spreads over here. And again looking at many levels, and here we have a node. So this node is here having k children. Each of these k children is again having k children, and each of those is again having k children. The probability of infection here is p. I know that there are k people at this level, but what are we interested in now is, out of these k people, on an average, how many people are infected here? And we know the answer, right? So if there is a person here and he has k neighbors, each of the edge has a probability p of infecting. So we have looked at it previously that there are going to be p plus p k times, that is on an average p into k people are going to be infected at this level. What about the next level? How many people are now going to be infected at the next level? Can you pause this video for 2 minutes and then try to figure it out by your own, and then you can resume the video. Now here I'm having p into k number of infected people. Let's say these are those infected people. So one is here, one is here. So here are p into k number of infected people. What happens next? This person here, how many people is it going to infect in the next level? Again the question is the same. One node is infected here and this node is having k neighbors. Each of the neighbors gets infected with probability p. As before, on an average, it creates P into K number of infected people. Similarly, this node here creates P into K number of infected people. And how many such nodes are there? P into K such nodes are there. So, how many people get infected at this level is P into K plus P into K and P into K times, which is P into K square. What happens at the third level is again similar. So let's say these people are those pk square number of people who are infected. So now on the next level, how many people will be infected? So each of these guys over here will infect on an average p into k number of people. So in the next iteration, pk plus pk plus pk, and there are p square people. So we add it pk square times and we get pk cube. So in the third level, pk cube number of people gets infected. Similarly, what happens at the ith level is pk to the power of I people get infected. I think it's clear now. So in this tree kind of a network, at ith level, we have how many people? We have k to the power I people. And then if we talk about the number of infected people, there are pk to the power I number of infected people. This is all about the basic epidemic modeling, and this model which we have discussed about, this is known as the branching model. So this model, it is known as the branching model. Looked at this example. Always keep this example in your mind. So one person having k children, each of these having k children, and then we looked at the branching model here. We found out the expected number of people infected at the ith iteration is p into k to the power I. What I said in the beginning, why are we studying these? Why are we studying this contagion? How does a contagion spread? And the answer was to understand whether something goes epidemic or not. When will I say something has become epidemic on this network shown over here? I keep going down in this network, and when I go a lot of down, let's say to some infinite level, and I see a person infected here, I can say that this disease has become an epidemic. If it was not to become an epidemic, it would have died somewhere here. But this disease starts from here, infects these people, infects some of the people at this level. We keep going down, and it even infects some of these people at too much bottom, or let's say at the infinite level. Then I say that this disease has become an epidemic. Now from all the information I have given you, that there are some probability p and number of neighbors k, p into k to the power I people infected at the ith level. Can you tell me whether this disease is going to be an epidemic or not? So based on the values of p and k, can you comment about whether a contagion is going to be epidemic or not? Is it even possible to say it? And the answer is yes. And in the next lecture, we'll see how do we do that. How? Just by looking at the value of p, the probability, and k, the number of children every node has, we can comment about whether this contagion is going to become an epidemic or not.